Let's talk about how TV works. We're first of all going to talk about how an older style TV works. You probably had these when you were younger kids. They were the televisions that had the big thing that stuck out the back. We'll talk about that. Then we'll talk about how a modern HD screen, flat screen, works. At the heart of every old TV was something called a cathode ray tube. We abbreviated that as CRT. It was named that before scientists knew what was going on. Cathode rays are just electrons. It's an electron gun, essentially. A cathode ray tube can fire electrons in a relatively straight line. So a CRT is a cathode ray tube. In the simplest cathode ray tube, a beam of electrons is accelerated by one set of plates and then deflected by another. Let me zoom in. What we would do is we would charge this side up very, 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 very negatively. Like charges. And so electrons would just bubble off of here. They would get repelled off of here. We keep sending more electrons in from an outside voltage source. So we could have a lot of electrons here, and they would just zoom off into the air. Now, what I didn't include, because it gets messy, don't write this down, we would also put a negative plate here. We would also put a negative plate here. That would push the electrons towards the middle, and you would basically get a beam of electrons. We would also charge this positively to attract them, and we would just have a small slit right there that the electrons could get through. So although you'd have kind of electrons bouncing around here, you'd end up with an electron beam. That was step one. Then what we would do is we would have deflecting plates. So if an electron came through here, what's the top charged, positive or negative? What's the bottom charged? It's going to get deflected up. What if we flip the voltage? Get deflected down. Now, what we also did, and I couldn't do this because it's a 3D diagram, we also would have had a set of deflecting plates on the outside towards us and behind inside the page on the other side. So not only can we deflect this electron up and down, we can deflect it left and right as well. In other words, we can put an electron, by varying the voltage of these deflecting plates, we can put an electron wherever we want. Then we had the screen. Here on the screen, on the interior of the screen, we had it painted with a phosphorescent paint that would glow when an electron hit it. So if the electron kept going and it hit right there, donk, that would glow bright white. You do that a bunch of times, you get an image. Each of those is 1 pixel. So it was a pretty low-tech approach, very clever approach. I think I have a more detailed one here. Sure. Put your pencils down and look up. Let's bring in Professor Whoopi, how a TV works.
But there's still something I don't understand, Mr. Whoopi.
Well, what's that, my boy?
I looked real close, and I didn't see any picture going across the room between the camera and the TV set.
But of course you didn't. There wasn't any picture, just electromagnetic waves which are invisible.
But then how...
How does it get to be a picture again? Well, let's go back to the 3D BB. Inside every TV set, there's a big tube. You call it a picture tube, but the correct name is cathode ray tube. It takes the waves from the transmitter and turns them back into electrons. In the back of this tube, there's an electron gun which shoots the electrons at the front of the tube. The front of the tube is coated with a special chemical which lights up when the electrons hit it.
And here, these are the deflecting plates. 2 of these would deflect it left-right. 2 of these would be deflected up-down. You can put an electron wherever you want.
And this is what makes the picture.
I get it. The orthicon tube turns the picture into electrons, and the cathode ray tube turns the electrons back into the picture.
Precisely, my boy.
Now that was for black and white TV. Color TV, all we did is we added 3 electron guns. Initially, it was called the RGB, the red, green, blue system. You would have one that would cause it to glow red, one that would cause it to glow green, one that would cause it to glow blue. But as long as you're far enough back, your eyes just blend the colors. So that is how a CRT works.
How does the monitor work? Signals from your computer's video card are loaded into 3 electron guns at the base of the monitor. There is one gun for each of 3 colors: red, blue, and green. These 3 colors, when mixed together, can create all the colors you see on your screen.
So this would get charged very strongly negatively. Electrons would bleed off. We would probably have a negative plate right there and right there to push the electrons towards the middle, get a nice straight stream.
Now, these guns don't shoot bullets. Instead, they shoot a powerful beam of electrons towards the face of the monitor. The beams pass through the deflection yoke. It uses magnetism to bend the electronic beams so they can sweep across the entire screen and create the picture we see.
What happens once the beams have swept your monitor? Special chemical phosphors are painted on the inside of the monitor. Energy from the electron beams makes the individual phosphors glow either red, blue, or green, depending on the type of phosphor. The stronger the electron beam, the brighter the phosphors glow. A sheet of metal with holes in it helps keep the electron beams aligned exactly with the phosphors. This is called a shadow mask. The beams sweep across the entire screen 60 times per second. It happens so quickly that you are unaware of the firing process. Instead, your screen appears to be a steady, continuous image, just as it does now.
So let's dive into this a bit more. Below is a side view of a cathode ray tube and a front view of a CRT screen. So we're going to imagine that you're the person sitting in a chair looking at, here's your TV. When everything is turned off except for the electron gun would hit right there. If you ever see an old black and white TV from the 1950s, when you first turn it on, there's a big dot in the middle that just stays there because everything had to warm up back when it was vacuum tubes and things like that. Or if you see a TV show that's set back then, they'll show you that there was a big white dot. Okay. Where will the electron dot end up? We're going to choose from picture A, B, C, D, or E on the right if we make the upper deflecting plate positive. So I'll just draw in here because I can erase this. If we make that positive, how would that deflect? Don't draw that in here because we're going to be doing all sorts of stuff. How would that deflect the electron? Like charges and unlike charges. So as the electron moves through the yoke of deflection, which way will it get bent? First of all, which way will it get bent? Up, down, left, or right? Like charges.
Oh, no.
Okay. Yeah, it's going to get pulled up. In fact, it's going to hit location A. You can put a dot right there. What if you made this deflection voltage stronger, higher? What if you make the deflection voltage lower? Right there. Okay, let's reset everything back to 0, 0. What if we make the right plate positive? So what if I made this positive? Well, that would pull it relative to us looking at this document into the page. What would the viewer sitting in that chair see the electron hit? A, B, C, D, or E? It's not D. Yeah, it's right. That back plate is like charges repel, unlike charges attract. The positive is going to attract. It would get pulled towards that back plate. This person would see it hit location B. What if we made the right plate and the upper plate positive? What if we made that one positive and this one positive? Where will it end up? E. Yeah. So you can see this gives us pretty good control over where we want to put an electron. Let me pause the video. So that's a way that we can control an electron. Next, supposing we adjusted the voltage so that at the beginning, I think we just turned the page. Did we not, if you're following along? Come on, people. It's called an attention span. Thank you. Suppose we adjust the voltage, so instead of the voltage of the electron beam hitting dead center, suppose the 0, 0 position is right here. We've adjusted it so it's already moved up a bit. Where will the electron dot end up? We're going to choose between A, B, C, D, E, F, and G. What if we increase the deflecting voltage? where will it end up, do you think? If we bump up the voltage, where do you think it'll end up? Yep. Gee, yeah, we're already deflecting it somewhat. Bump it up, it's going to end up even more deflected. Okay, let's put it back to here at the beginning. What if we reverse the polarity of the voltage? We make the top positive and the bottom, or the top negative and the bottom positive. Where will it end up? Yep. Yep. What if we increase the accelerating voltage so the electrons are moving faster through the deflection yoke? If they're moving faster, Noor, do you think they'll get deflected more, or do you think they'll get deflected less if they move through there in less time? Yeah. So if we increase the accelerating voltage, that would move it to location A. It won't get deflected as much. So we have several ways that we can, right? Niels, if it's moving faster, it's not between the deflecting plates for as long, doesn't have as much time to experience the force. Okay. Pardon me? You'd get a brighter dot on your end. Yeah, but that we're just talking right now about position. But now we can also then talk about how we can show gray or black or white for the old black and white TVs, or RGB. We can show bright red, dim red, no red. Yep. Okay. So in what way does our simple model of a CRT explain how a black and white TV works? So the person would be sitting right here. We have a set of Y plates that deflect the electron vertically. We have a set of X plates that deflect the electron horizontally. So only one dot is hit at a time, and it'll glow. By sweeping the Y voltage from negative to positive, what we can do is we can paint one stripe vertically. Then we bump the X voltage up by a tiny bit. We move over 1 pixel. We paint another stripe vertically. Move over 1 pixel, bump up the X voltage again, another stripe vertically. And so what you end up with is this: paint, 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 except much closer together with no gaps. And we got clever. Rather than always paint in one direction, when we get to the bottom, we stay at the bottom and just sweep our way back up. That made an image smoother, and you get an image on the screen. And you do this 60 times a second. That's enough that your eye can't even detect the motion. You see a moving image, not a bunch of stripes on the screen.
So when you're that like wave feeding, let's say the
Yep.
person is putting the magnets on the TV or just directed.
Yeah. Yeah, because we hadn't yet. So yeah, we learned that also these moving electrons get deflected. In fact, what I used to be able to do with the old TVs, so I don't know, there might be the odd teacher that still has a big VCR cart with an old style TV in their room. Those have mostly gone away. But I used to have one. I would put a piece of tin foil on the TV screen when it was on, and I could clip wires to this corner and this corner, and I could get current because it was electrons. I may as well use it.
Upstairs.
Yeah, yeah, they're still kicking around. Yeah. What's really cool when you see that looks like a snow blizzard, that's actually cosmic microwave background radiation. You're seeing the echo of the Big Bang because those charges are still moving all around us. Not at a high enough level once the TV is on to affect things very much, but when nothing's on, that's what you're seeing. Yeah. It's very cool. So then we step the beam over using a small X voltage. Boom, boom. I knew I had this picture somewhere. This is what you get. Okay? We gradually add increments of horizontal voltage, sweep vertically, we illuminate the higher screen. The TV signal turns the cathode ray beam off and on as it sweeps the screen, so the signal coming in would just have no energy at one point. That'll be a black dot. No electron would get fired. Oh, now there's energy. Now it'll fire an electron. It takes care of itself in the same way when we made the loudspeakers. The music took care of itself. As long as you hooked your source current up to the music, It took care of everything as long as you hook your source current up to the TV image from the camera. And inside the camera, by the way, he talked in that Professor Whoopi old cartoon about the autocon tube. It's basically a tube inside the camera that reacted to light hitting it and gave off a current. So you would get a current directly proportional to the image that the camera lens was seeing. You would have to amp it up because it was a really tiny current, run it through your system, send it to a TV, and it all takes care of itself. Very analog. Very nice. So the TV signal turns the cathode ray beam up and down as it sweeps the screen. Beam on is a white dot, beam off is a black dot, beam partially on, low speed is a gray dot, and you get a picture. Actually, that was the original, but what we actually do instead, rather than using these parallel metal plates to deflect, we use solenoids, because solenoids, you could put them vertical and horizontal. It dramatically shortened the back of the TV. So what we actually had is a solenoid here. Now this vertical solenoid actually does a horizontal deflection. I'll prove it to you. The magnetic field right there is either pointing straight up or pointing straight down. We have an electron coming out of the page. That's the same as a proton moving into the page. If the magnetic field is straight up, the proton gets deflected relative to us to the right. If the magnetic field is straight down, the proton gets deflected relative to us to the left. So the vertical solenoid was a horizontal deflection. Oh yeah, because everything was perpendicular in this unit. That makes sense. And this horizontal solenoid gave a vertical deflection, and that managed to shorten the back of the TVs by quite a bit. You didn't have to have these long deflecting yokes. You could do it in one little section. So solenoid M, which is vertical, can deflect the electron horizontally. Solenoid N, which is horizontal, can deflect the electron vertically. TVs. Now, how do LCD screens work? Put your pencils down, look up, and I think I have to stop the video because I'm pretty sure I'll get a takedown note.